Okay, calculus. I already went over 8 from page, I don't know, even just a second, from page, I already went over 8 from page 469, but someone asked me for 1, B, C, and D, so I'm going to do those as quickly as I can. 469, number 1. So it's just find the derivative. So for B, it's y is equal to log 5 of 9x minus 7. You can't take the derivative of a log, only ln, only a natural logarithm. So the first thing I would do is I would change this into logarithmic or into exponential form. Sorry, was in logarithmic form. So I would change this into exponential form. Then I would take the ln of both sides. I'd use my power rule. I'd bring the y down in front. And then I would do the derivative. Here, I would have to do the product rule because this would be f and this would be g. So g f prime. So the derivative of y is 1, but I have to say I did the derivative of y with respect to x, plus, then we leave f alone, but we do the derivative of g. Now I've said before, if you have ln of a constant, because it's a constant, and the derivative of a constant is 0, then the derivative of ln of a constant is automatically 0. And that's equal to ln of 9x minus 7. The derivative of ln is 1 over whatever I'm taking the ln of, which in this case is 9x minus 7. Then I take the derivative of what's inside, which would just be 9. So currently I have ln 5 dy over dx equals 9 over 9x minus 7. The only thing I can do here is I need to get dy dx by itself, so I'm going to divide this side by ln 5. So that means I'm going to divide this side by ln 5. So I really have 9x minus 7 times ln 5 on the bottom. That's gone here, and that is my answer. That was 1b. 1c is y is equal to 3 to the x. Okay, well that's already in exponential form. So I think I would take the ln of both sides, because I can. Use my power rule to bring the x down in front. So I have x ln 3. So on this side, the derivative of ln is 1 over y. But the derivative of y is dy over dx. On this side, there's your f, there's your g, so that would be the product rule. So g f prime plus f g prime. But again, it's ln of a constant, so that derivative is going to be 0. So really, I have 1 over y dy over dx equals ln 3. I'm going to multiply this side by y, so my y's cancel, and I just have dy over dx. That's going to give me ln 3, and that's all one piece, times y. But up here, at the very beginning, it said y is 3 to the x. So I'm going to replace the y with a 3 to the x, and that would be my derivative. D is going to be done exactly the way I did B. So in D, it's y is equal to log 4 of x squared plus 3. So again, that's in logarithmic form, can't use it, so I'm going to change it. 4 to the y is x squared plus 3. I'm going to take the ln of this side. I'm going to take take the ln of this side. I'm going to use my power rule to bring my y down in front. So now here's f, here's g. I'm going to do my product rule. So g f prime, which would just be dy over dx, plus f g prime, but the derivative of ln of a constant is just 0. That's equal to the derivative of ln is 1 over whatever I'm taking the ln of, and then I have to do the derivative of the inside, which is 2x. So I have ln 4. Why did I put an I? That's weird. So I have ln 4 dy dx equals 2x over x squared plus 3. So I'm going to divide this side by ln 4 so that the dy dx is by itself. So that means I'm going to divide this side by ln 4. And so really what I have is 2x over x squared plus 3 times ln 4. And that would be my derivative. All right. So those were the questions that I had given to me. So I already went over section 7.8. That is the homework you are probably currently working on. I'm going to jump ahead to section 8.3. Section 8.3 deals with limits of trig functions. So limits of sine, cosine, tangent, those things, all right? These are things that really you just memorize. We're not going to use them very often in this course. I go over them so that you've seen them. Really, you end up using them more in first year, second year calculus is where they really show up a lot. But I just like to be able to say you've seen them before I send you off to university, especially for those who will be doing this again. All right, so let's think about a sine graph. If you can remember, a sine graph looks like this, and a cos graph looks like this, right? It starts at 1. At 0, it's 1. And this one, the sine wave, at 0, it's 0. All right? Now, when we do limits, technically, you always do limits in radians. Now, that's not going to matter for what we're doing, but normally you would always do limits of trigonomic functions in radians. You switch your calculator over to radians. So we're going to talk about just some basic limits, and then I'm going to show you how you would actually use them in a question. Now they do bring in a couple of trig identities. You are not going to have trig identities memorized. If you still have your sheet, it might be handy to have out, but again, you're not going to be using it really in here at all, okay? I'm going to refer to a couple because of the examples that they do. However, I try not to put them in the work that you're doing, all right? So the first limit they talk about is they talk about what is the limit as x approaches 0. So here's my x, here it's approaching 0, for sine x. Now they don't use x, they use theta, but it doesn't really matter, okay? And really just by looking at the graph, we can tell that as we approach 0 from either side, as we approach 0, the y value is approaching 0. So my limit as x approaches 0 for sine x is 0. Now, my limit as x approaches 0 for cos x, okay? So as I approach 0 along my x-axis, as I approach 0, and again, this would just continue. As I approach it, doesn't matter which side I come at it from, as I approach it, it is approaching 1. So I've just given you 2 limits, and they're really 2 limits that just come off of the graphs that you already know, or at least I've seen before. Now, there's a couple of other limits that, again, can be proven if you put your calculator in radians, but I'm just going to give them to you. Okay, there is a limit as x approaches 0 for sine x divided by x. Now this is one where it would be really important that your calculator be in radians, okay? So radians go from 0 to 2 pi, 0 to 360. They go beyond that, but that's the standard that we use. So if you use, say, pi, if you did sine of pi divided by pi in your calculator and you had it in radians, it would spit out an answer. Now they want to know as you approach 0, and we know we can't put 0 in here because there is, that would put 0 on the bottom of a fraction. So you can't put 0 there, but, excuse me, but you could put something close to 0 there. Again, to do it, your calculator would have to be in radians. So you'd pick like 0.01 or 0.001. Pick something close to 0 in just put your calculator in radians, put it in. What you would find is that your answer would be close to 1. So the limit as my x value gets close to 0, can't be 0 because you can't have 0 on the bottom of a fraction, but close to 0, your answer would be close to 1. In example 1, they give you another limit, and really all they do is do a table of values to prove it to you in example 1. That's all they're doing. So I don't bother to do it. They give us a limit as x approaches 0 for cos x minus 1 over x. And again, we know that x can't be exactly 0 because that would put 0 on the bottom of a fraction, but what if we got close to 0 in radians? What would my answer be? Turns out my answer would be 0. So there's another limit. So these are sort of like trig identities. They're things that you just kind of know. All right, and let me now show you how would you go about using any of these? I just want to make sure I have them all. 1, 2, 3, 4, 5. Oh, there was one other one, but you don't see it very often. So the counterpart to this one, the limit as x approaches 0 for cos x over x, instead of the cos x minus 1, just cos x over x, it doesn't exist. Because if you go close to 0 on the negative side, or if you go close to 0 on the positive side, you actually end up with 2 different answers. Remember your left-hand and right-handed limits, if they're not the same, it means it actually doesn't exist. So I will talk about any trig identities that they use. I will let you know that they're using it and just remind you of it. But they're not getting into the really complicated ones. It's not going to be like proving identities. Don't worry. Okay. So example 2, there is an A, a B, and a C. And we are going to do all 3 of them. And we are not going to do example 3 because example 3 is just proving that this does not exist. And again, all they do is a table of values. So we're just doing example 2, page 506, A, B, and C. And again, I will let you know what trig identities they're using when. So they want to know the limit as x approaches 0 for sine x over 2x. Now let me explain how this is going to work. What you want is you actually want to break this apart in such a way so that you have some of these things that you know, and we will go with just these 4. All right? You want to break this apart in such a way so that you have some of these. So how I would break this apart would be this. Like this is like there could be a 1 in front of that, right? 1 times sine x over 2x. So I could actually break this apart to be 1/2 times sine x over x. And if my limit is that x is approaching 0, well, there is no x in this piece, so it just stays 1/2. But if my x is approaching 0 for sine x over x, and I know that my limit as x approaches 0 when I have a sine x over x is 1, I can just replace that with 1. And so 1/2 times 1 is 1/2. And so that's my answer. My limit as x approaches 0 for sine x over 2x is actually 1/2. So the answer to this is 1/2. And that's why. Again, I want to break apart the question that they give me so that I have one of these trig identities that I know. All right. Example 2b gives sine 2x over x, and it is my limit as x approaches 0 again. Now, if you look in the textbook, they actually give 2 separate solutions for how they do this. Solution 2 is hard to follow, and to me is not something I would ever think about doing. All right? Solution 1 is a place where I would actually want to know a trig identity. So back in grade 12 and you're in, when would you ever use these? Welcome to when you would use them. All right, here's how I would use this. Sine 2x, that's one of those double angle identities you had on your sheet. And again, I'm not asking you to memorize these all over again. But you had on your sheet that sine 2x is really 2 sine x cos x all over x. All right? Now, again, I'm going to want to break this apart in such a way so that I have some combination of these. So, whoops, x approaches 0. So I could break this apart so that we have 2 times sine x over x, because I have an identity for that, times cos, because, I have a limit for that, and I have a limit for that. So this and this are exactly the same thing, right? I just broke it apart in 2 pieces. So now when I'm talking about my limit as x approaches 0, well, for this piece there is no x, so it just stays 2. For this sine x over x, the limit as x approaches 0 is actually just 1. And for this, my limit as x approaches 0 for cos x is actually just 1. So I have 2 times 1 times 1, which is 2. So my answer for that is 2. Again, they do it in a way that they call using first principles for solution 2. If you want to look at it, feel free. To me, it is much, much more confusing. And this is a place where knowing a trig identity would actually make your life way easier. Last one, and this is all I'm doing for today. Isn't that wonderful? Last one is my limit as x approaches 0 for 3 tan x minus sine x all over x cos x. All right. Here is where they use another identity in this one. They use an identity that we talked about a lot when we were doing trig identities. And that is that tan x is equal to sine x over cos x. All right? So, just so you know, that's going to come into play here. So again, if I ask you to do something like that, it's going to be some of these simple trig identities, not some of the really weird ones that you don't remember at all. If you don't remember any of them at all, hopefully you still have your sheet. If not, they're on the internet. Go look them up. So the strategy here is to express the function in terms of sine and cosine, because look, all the limits I know have sine and cos in them. None of them have tan in them at all. All right? So what they did, and I'm going to write it out a little bit differently than how they did it, okay? I will likely do it differently than how they did, because I'm not really a fan of how they did it. This would be 3 sine x over cos x minus sine x, right? That's the top, all divided by x cos x. Now, to me, I would think about common denominators here, right on the top. So 3 sine x over cos x. I would need a cos x on the bottom here, so that means I'd have to multiply the top by cos x, so minus sine x cos x, all divided by x cos x. All right? I would rewrite this. I'm running out of space. I would rewrite this as 3 sine x minus sine x cos x all over cos x. So keep, switch, flip. So times 1 over x cos x. So I'm going to go back up here. So on the top I have 3 sine x minus sine x cos x. On the bottom I would multiply cos x times x cos x, and that would give me x cos squared x. All right, now I could take out of here a sine x on the top as a common factor, and I would have sine x times 3 minus cos x all over x cos squared x. Right? They've done this, but in a more roundabout way. They don't explain themselves as well, but they are now with me. Okay, they're with me now. They're like 3 or 4 steps down. They have this the same as I do. All right, so now what I would do is I would actually break this apart. So I would have sine x over x, because that's a limit I know, times 3 minus cos x over cos squared x. And it's at this point that they say that you can start replacing things. So remember, my limit is that x is approaching 0. So for sine x over x, that's 1, times 3 minus, now what is the limit as x approaches 0 for cos x? It's actually just 1, so I'm going to put that 1 there. And this is cos squared x. Well, for cos x, it's 1, so this would just be 1 squared. So 3 minus 1 is 2 over 1 squared, so 2 over 1. So this is really 1 times 2, which is 2. Now that's a pretty complicated one. I'm likely not going to ask you anything that difficult, especially on a test or something. I'm getting you to do only 3 of these, 3 pretty straightforward ones, all right? I'm getting you to do 3 pretty straightforward ones. None of them should require any trig identities at all. None, all right? And that's all I'm getting you to do, just 3. Your homework should take probably 5 minutes max, all right? And then we have one more section to do, and that will be it. We won't have any more to do. So only 1 or 2 more videos max, and we'll be done. I have that we should be able to do a test Thursday of next week. I think we'll even be there a little sooner, but I'm willing to wait until the Thursday to have it done. I'm still working on your assignment to get uploaded, so even if we put off the test until Thursday and we don't have any new work, that gives you lots of time to study and prepare for it. The test will be on like the last part, the part of chapter 7 that we've done, which is on logs and longs and all that good stuff. And then on this chapter 8. The last section will take at least a couple of days to get through because of really the second example is kind of fun. I like it, but people freak out at me. I actually like it because to me it's like, it's not like trig identities in any way except that it's like a puzzle I get to solve. So I enjoy the challenge, but a lot of people just think I'm crazy. Probably am. So we will finish up, what's today? Well, you're watching this on Thursday. So yeah, so Monday, Tuesday, and yeah, easily test on Thursday is not a problem at all. So test on Thursday of next week, and that will be the last thing we're doing for calculus. You will be done other than the assignment. All right? Have a good day.